31, which is AC circuits, okay? So this first part is on AC sources and phasors. And so if you have a DC source, right, it looks like this, a very boring graph, okay? This is your voltage, all right? So this could be like 5 volts or 3 volts or 12 volts or 9 volts, okay? And it's constant. It's just the same voltage all the time, okay? So if you plot it versus time, it's a very boring graph. It doesn't change very much, all right? This is what an AC source looks like over time, okay? So it's oscillating. Here's your peak voltage, your peak EMF, right? And what kind of wave is this? This is cosine, okay? So if you want to write it out as, instead of just E equals E naught, right? It's E equals E naught cosine omega t. And what's omega? It's radians per second, but it's the angular frequency, right? So it has to do with this, sort of the period. So it's 2 pi over the period, okay? So if you make your angular frequency larger, what happens to the period? It's smaller, right? So bigger omega, the graph gets more smushy, and you get a higher frequency, all right? Okay, so this voltage oscillates between this maximum and this minimum, all right? And the oscillation period is just going to be 1 over the frequency, which is 2 pi over omega. Omega is the thing you see here. So we're thinking back to sinusoidal stuff. Now we're going to introduce something that you are not familiar with. Okay, this is just a sine wave. We remember that from simple harmonic motion. We've talked about it in terms of LC circuits. It should be pretty familiar. But let's talk about something called a phasor. I know this is not like a gun from Star Trek. Okay, so a phasor, that's a vector, right? Remember, any sinusoidal motion comes from circular motion, right? If it's periodic, you can map it onto a circle. So we're going to map the phase onto a circle. So a phasor is a vector that rotates along the unit circle, right? So it starts at the positive x-axis. This would be an angle of 0, and it rotates this way, okay? At an angular frequency omega. So it follows the same frequency that you would have in your sinusoidal graph, okay? So for instance, here's our phasor, all right? And you can see it maps out on the circle, so the magnitude of the phasor stays the same. What is this angle from here to here? What's it going to be? What?
Like 45-ish?
Oh, no, not specifically. Like, how do you get that from the previous slide? Like, what would it be in terms of? Omega t, right? This angle is omega t, which means this going all the way around, what is that? What's that in terms of the period? You go all the way around the circle. 1 period, right? You go all the way around the circle. That's 1 period. Okay. So the other thing you want to think about is the projection along the x-axis is going to be E naught omega t. Okay. So you can map this back to what you're seeing on the graph if you want to figure out the amplitude at that time, right? Look, the length of this doesn't change, but the length of the projection on the x-axis does, and the amplitude is the projection onto the x-axis, okay? So you can see it starts at maximum amplitude. This is cosine, right? So when you start, your phasor is along here at time equals 0, okay? As it starts to go like this, you can see it gets smaller. When it gets here, what's the projection onto the x-axis at omega t equals
0.
It's 0, right? So that's when you cross. Once you go over here, it's negative, right? It should start out small, and it should reach a maximum negative at pi, all right? And so then it does that again. And so this is going, the projection along the x-axis maps out what you see in the cosine graph, okay? And so it kind of looks something like this, right? If you want to plot it visually, all right? This projection graph is sideways, mostly just because it looks better. But you can see, as you go around the circle, you're mapping out this cosine wave. Okay? So if you think about this in terms of how you plot these things, here, at the maximum amplitude, this is where your phasor is directly along the x-axis. Okay? When you get over here to a quarter of the period, all right, that's going to be at omega t is equal to pi over 2, which looks like this. So you have a projection up, and you can see the amplitude here is 0. Okay? Then if you get to half of the period, which way does your phasor point? Left. Okay? So that's for omega t is equal to pi, right? The angle's pi. And then your amplitude is going to be negative maximum amplitude. All right? And so on and so forth. All right? So you go all the way around the unit circle. Here you've made it all the way, omega t is 2 pi. That's the whole period. All right? So why do we even, so this phasor thing is new. Why are we introducing it? For AC circuits. What do you think the phasor has to, like, what word is in phasor? Phase, okay? And what's tricky is different sine waves can have different phase, and we need a really easy way to keep track of that, because we know phase is just shifting the wave back and forth. But if you're just looking at a sine wave on top of another sine wave, is it easy to figure out what the phase is? Not really, right? Unless the phase is something like pi over 2, where you can see that it shifted from cosine to sine, right? It's not easy to determine what the phase is just by looking at two sine graphs mapped on top of each other. So the phasor does that for us, and it's a lot more visually easy, okay? And so we'll get there in a second. But which way does the phasor rotate? Counterclockwise, right? It goes along the unit circle. So if you want to predict the future, you know it's going to be moving counterclockwise. All right? So here's a question. And what do we mean by instantaneous value? Increasing, decreasing, or constant? Please discuss.
Increasing because it's going down.
Uh,
Shoot.
Is the answer is increasing, okay? Because look, we're looking for the projection on the x-axis, okay? So at this time, the projection would be about here. As this thing moves towards the x-axis, it's going to get bigger. So the instantaneous current, meaning the current you measure at that particular time, should get bigger as this thing moves in the counterclockwise direction, okay? So this is just introducing what phasors are.